Okay, good morning to everyone. Here's Gilberto Thomas again from Brazil, and today I'm going to teach you about some two new tools available at CompuCell 3D, which allows you to visualize better the simulation you are doing. Okay. One of that is the vector fields, which provides you a set of tools to show uh, uh, you the evolution of your system in the simulations windows. And the other one is the AdhesionFlex plugin. It's a kind of different plugin, but it's very helpful when you have in your simulation your energies, their contact energies, to deal with more adhesion molecules than one. For example, you take into account integrins, caderins, N-caderins, E-caderins, any kind of adhesion molecule you need, you may implement them through this AdhesionFlex plugin. A reminder that this workshop is live streamed, recorded, and will be distributed by you in YouTube. Okay, let's go. The first topic is the extra fields. This is the outline of this first part. I will explain a little bit what is a field, with what kinds of fields you can find in nature or to represent this, and its implementation is CC3D, the scalar fields, a vector field, and both in the same simulation. We are going to use simulations already done in the previous lectures to implement these fields to save time. Okay? Well, what is a field in physics, of course? Field, not in agronomy. Field is, in physics, is a concept that is used to describe the space where your system is defined. If you have a deformation created by this system or part of the system in the space, we can use the field representation to visualize how this deformation is evolving in space and in time. Okay, examples of this kind of fields, we have gravity here. We have, for example, magnetic field, magnetism, see? And we have heat, are examples of fields, but they are physically much different each other. Okay. See, in the magnetism, the block is suspended in air, just being supported by the magnetic field created by these plates below and above. Okay, let's move. So let's define the difference between those two kinds of fields. The first one is the scalar field. In the scalar field, each point of the space is described by a number, a single number, a scalar. For example, we have here a picture of the sun, and the sun is spreading heat over the earth, and this heat of the earth can be mapped in the right picture with a color scheme, for example, to represent what is the temperature in each region of the map. Okay, we just need the numerical value to describe these fields, nothing else. Another example is the pressure field. We can go underneath the water in the ocean, for example, and describe the depth of the ocean, the pressure of the depth of the ocean with a single number, which is increasing as long as you are going deeper and deeper. Okay? So just a number is needed for a scalar field. On the other hand, we have the vector field. On the vector field, the space is described by a vector. Each point of the space is described with a vector, a single vector. A vector is a scalar which has associated with it oriented direction. Here we have the gravitational field as example. In, in the middle picture here, you have a single person here, and the arrows are representing the gravitational field at Earth's surface, like as if we were parallel uh, mm, uh, vectors. But this happens because of the Earth's curvature, which is very high. The radius of the Earth is much big, so we can approximate the surface of the Earth as a plane. In this approximation, the real gravitational field, which would be radial inwards to the Earth, is represented by a series of parallel lines, like the uniform field. Here we don't have a uniform field, a constant field. Here we have a radial field, which is the real gravitational field. This is an approximation because of the size of the Earth. Okay, so a particular type of the field we are much interested in is the velocity field. Velocity field not only describe the space, not describe the space, but describe how the, the constituents of your system evolve, move in that space they are located in. Okay, they with the help of the velocity field, you can see the flow of the system, for example, of the constituents of your system. For example, here we have these clouds moving around, but in this picture, in a very good big map, you can see a velocity field of the clouds moving in a bigger region. Okay, we are mapping the motion of these clouds with a set of vectors which describe the movement of these clouds. And then you can see how the wind, for example, behaves in that region. Okay, let's go on. Here we have more examples about the velocity field. And the first one here, we have, I have to wait a little bit here. Okay. An example of that model that Pedro has shown to you in a CC3D simulation, the VCheck model, the anemoid models. We have a flock of birds flying together, make these beautiful movements, and this you can map with the velocity field. Here also we have a herd of ships moving as if you can tag to each ship a vector, and you can see the field velocity, the velocity field from this movement of the herd. In this one, we have the flow of a liquid, for example, inside a tube. And you can see the boundary layer described because the flowing of the particles of the fluid is lower near the borders of the channel, and it increases towards the arc, the center of the tube. And these other two quick moves here are the movement of cells in a layer. This is a MDCK cell monolayer moving, and you also can describe each cell with a vector, a velocity vector, to describe the whole sheet moving. Finally, this other one here, there is a movement of cells closing a gap, maybe a wound healing experiment here. Cell migration towards an empty space in the petri dish, maybe, and you can attribute to each cell a velocity vector to describe the movement of the whole system. So now you have those examples, and you are going to implement that with CompCell 3D. These extra fields, so in CompCell 3D, helps you to visualize the evolution of individual components of your system. Okay, and the CompCell has a special steppable to implement such fields. This steppable is called extra fields. You can find it in the help, the manual pages of the CompCell, searching here for extra fields, and you have these instructions here. I should mention that the addition of this special stackable is not made in the simulation wizard. If you see here the reproduction of the wizard, there is no extra fields here. Okay? But where it is, it's here. After you build your code, you go to CC3D Python tab, and in the drop-down menu, you will find the extra fields inclusion. Okay? Of course, you have before, I will tell you how to do that. There is also in this drop-down menu the add steppable expression, the inclusion of the steppable you need to extra field. Okay. Let's see how to implement this extra field then in CompCell 3D. We are going to do that in using some previous simulations. Let's say first this exercise of lecture 2.3. In the example 233, the cell pressure or contact inhibited growth you have made few days ago. Okay? The one on you have a bunch of cells growing, and we regulated the pressure in the system by forcing the growth to be adapted for this function here. So the target volume of the cells goes to a constant value, and also the average pressure goes to an average pressure here, a constant one. Okay? So if you have this exercise in your computer, you can open it now, and let's edit it. Or, as if you prefer, you can download the exercise from the demo codes of day 7 in the students' materials, the exercise 7.1.1, and we follow the edited simulation from the beginning. I think we have to go this way to save time. Okay? Anyway, I will show you here. Let me decrease a little bit here to come with this to edit. In the to edit, I have loaded already both the exercise, the 2333 and the 7111. They are already edited. Okay. So first thing, after you go to the previous code if you are going this step. I should wait a little bit for you to load these codes in your two edits. I will give you 2 minutes. If you are using the old one, the 2333, after loaded, you must save it with another name to not lose that one. Give you what name you want. After saving, you go to the if you are going to start with the old one after save it to another name, any name you want, you go to the drop down menu here of CC3D and add a step. This is we will open this window here, and you have to give the steppable a name. I named it like this one. Let me show you here the name I give it. It is included at the end of your new of your file steppable with the name of extra field visual steppable. That's the name I gave. Okay, so and you have also to choose from that window the kind of field you are including. Okay, if you want a vector field or a scalar field. Well, let's now include a scalar field for now. Okay, so click in the scalar field and scalar cell level. I have to explain that. If you want to use scalar fields, you can use scalar fields for each pixel of your cell, or you attribute a scalar field, the value of the scalar field, as an average to the center of mass of your cell. Okay, let's choose this one, scalar cell level, and click OK. When you click OK, you have all this new class included in your steppable files, and also in the main Python file, this one, a new line with this steppable is included here. Remember, the steppable file, the main file is the one who called the steppable file. If you are including anything here, any new class here is new steppable, this new steppable must be included in the main file, otherwise it will not be called from your simulation. Okay? So let's go. Once you have the steppable included, now you have to add the fields. Which fields is which fields? In this exercise, we are going to keep track of the pressure and the volume of the cells. Remember, we have these two windows here, one of the volume of the cell, another for the pressure of the cells, and these are the fields you are going to keep track. So we have to include two extra scalar fields in your simulation. And this is done by, again, going to the extra field drop-down menu. And in the init function, remember, the init function is the very first function you have inside your class here. In this function, you will include the new extra fields here. Create init function. You have to create two of those fields. I mean, you click one, then you open again, and I don't know, click one, it appears in this way, then you open again and click it again to create a second one. So this is the line that appears when you click there in the drop-down menu. Self-create scalar field, cell level, Python, and in between parentheses, the name of the scalar field you want to create. So here is what I did. I included this line and I gave it to the name, I put the field in a variable, in a Python variable here. Self-scalar field P equals that thing I just created, and with the name pressure. P for pressure, and the second one, V for volume. Okay? Let's get rid of that line. Now, once I have included the created the fields with a variable here, self-scalar field P, self-scalar field V, I have to define. Now we have this. Now here we have both here. We have now to create these placeholders in the step function for the fields. So in this array here, I will store the self-scalar field P. Field P is self-scalar field P that I just have created in the init function. And I'm going to be sure that this field is clear. I mean, there is no values at all at the beginning of the step. I will fill the field later. The same for the field V. Field V is self-scalar field V dot clear. So I have both fields empty of values right now. And then I will fill the fields with the actual values for the pressure and the volume for each cell in this loop here. Okay? So this loop is filling the field with the values of pressure and volume for each cell of your simulation, of your system, if you are. And that's it. Then you have now the fields created and the field being fulfilled with the values for each Monte Carlo steps. Then, for each Monte Carlo step, I empty the values, I clear the values, and I refill the fields with the actual values for that Monte Carlo step. Okay? So let's see here. Open in player. Where's the player? Time the player is. Oh, it's open in another window here. At the beginning, if you are using the downloaded simulation with 711, it's already built the fields graphical windows here. If not, for example, if you have changed the old code to the new one, this new Windows doesn't appear at the beginning. You have to open it from the Windows tab here and open the graphical windows you want to see in your player. Okay, so let's start over here just to give them a step. So you have now the cell field here, the system, the graphical windows with plots about the average target values and the average pressure for the system. And here, these two windows, the new windows, are the pressure field window and the volume field window. Put it to run. As soon as you start to divide, you have here a color bar indicating the pressure of each cell and the volume of each cell.
Excuse me, Gilberto.
Yeah.
I see in the code there is no command to begin those new graphs. They come automatically, or?
Oh, that's what I said. If you don't see at the beginning those two windows, you go to Window tab here and open a new graphics window. For example, here I will do it here. I can do that. So you open new graph here, and from drop down menu here you can where is the it's in another window. If you click in here, I have a bug in my player in the choice of the options that could appear in this drop down is in another screen. So I will click here in the pressure one, and you have a new window with that pressure field you want. Okay. If you stop the simulation, this layout will be saved in your file .sqlite in your simulation folder. So when you open the simulation again, it will appear right like that. Okay, Junior?
Okay, so creating a new field automatically gives another entry to a new graph, maybe.
Yes,
So
yes,
okay.
yes.
Sure.
Okay. So this is what you got running the simulation. You have both windows here for volume and pressure, two scalar fields showing you the evolution of your system. Okay? Let's go. Just to see, this is what I have said to Julie right now. You open here, new open graphic windows, and now I can do that. And create these two windows. And these windows will be left open after you stop the simulation because this layout information is saved in that SQLite file inside your simulation codes folder. Okay. Now the final image is that, and let's go to another example now. The vector field. Let's include a vector field. And for that, we are going to use one of the Julius exercise from yesterday, the exercise 611D, when he created many moving cells with compartments. Okay. So this exercise is the exercise E712.zip in the student's material day 7 demo codes folder. I will open here just to save the time. Close. Close. Okay. So this, remember, this is the demo, Julius demo, where you start with only one cell, and the cell starts to divide and proliferate. Okay. So we are going to do a few modifications on Julius code here at the nucleus lambda volume should be put equals to 4 in that exercise. And we are changing the limit of the number of cells to 16 to not quickly to fulfill all the grids very fast. Okay, here we limited this cell number to 16 to avoid much more cells. We have to insert in the code. I will open here just to show you. Of course, after you add the steppable, okay, here, or better, you are adding the steppable as a vector now, and vector cell level. Okay, you have to choose both. Click OK, and the steppable will be added to the end of your what is that? I lost it. No, where is my step? Here. I gave it a name, extra vector visual. The other one was extra scalar visual. This is extra vector visual. Okay. You are going to create only one field now, the velocity field, from the drop-down menu, in each function, you create a vector field, cell level, create init. Okay? Like that. Oh, I included in the wrong position. Anyway, it's here. Self-create vector field cell level pi, name of the velocity field velocity. And I give it as a variable at the beginning. Okay? So, now we have done this. So remember, from the lecture I gave you about keeping track of the speed of the cell. To keep track of the speed of cell, we have to know the position of the cell at 2 time steps different. So you need to include that cell dictionary to keep track of the old position of the center of the mass of the cell. It's here. Again, at the start function, I created this dictionary here to keep track of the cell position of any previous Monte Carlo step. Here I put 0, but whatever. I should put here maybe for cell font XCOM. Cell font YCOM. So at Monte Carlo step 0, the values stored in the dictionaries are the 0 position of nucleus center of mass. Okay, so the next thing is to to create a placeholder for the vector field. It's here. Field, self-vector field. I mean, I'm putting the variable self-vector field in an array that I will fulfill later. Okay? So, I also define a time interval to measure the displacement for calculation of the velocity, for the speed. This time interval equals to 100. And then at each Monte Carlo that divides by time interval has 0, I calculate the displacement del x and del y. Look if there is some correction to make, considering you are dealing with periodic boundary conditions here. Remember, we did that in the previous lecture. Then we calculate the velocity components here. Nucleus velocity x, nucleus velocity y, by del x over time interval, del y over time interval. And I fill the velocity field with those values. See, each component of the velocity field here has three components, x, y, and z. Since you are dealing with 2D dimensions, we are walking over a substrate, over a plane. We don't have any x components. It's 0 everywhere. But even so, you have to write here the three components, x, y, and z. And update the dictionary for now with the actual x cone and y cone for the nodes. Understood? Any questions? What is any old x and any old x are the positions of the nucleus center of mass in the previous Monte Carlo step. See here, when I calculate the displacement, I am calculating the displacement between the now position minus the old position. Okay? This is the way you calculate the displacement. And the velocity is this displacement divided by the time interval, the component of the velocity. Okay? Now we can save it here because I changed that thing. And I will put it to run. Open player. Where is the player? Thomas. See. I was stopping over. At the beginning, then I have the field velocity window here and the cell field here. Okay? Remember, this is a three-component cell. It has compartments. Let's go. See, this small arrow here represents the velocity of the cell. The color is the strength. You have to wait for the division. So slow today. This one doesn't divide. Okay. It's change all the time. It's not divided, why? Ah, okay. When the cell divides, you have two errors, one for each. Let's run a little bit to see the division. Okay, again, another division and an extra error. So if you keep long enough, now you have multiple cells divided because the number is growing. You have multiple arrows for the velocity field.
Gilberto, we have a good question in the chat. Why are the arrows changing colors?
Is the strength of the colors are connected with the modulus of the speed, actually, of the velocity. Because they are not moving with the same speed. So this difference is in the color of the colors of the arrows. Okay?
So in this case, red would be high and blue would be low, right?
Yes. I think you can, I think you can, I don't know how to do that, but I think you can here in the configuration fields. I don't know how to. This has changed this layout here. To see if we could add a error bar, a color bar with the speed.
Because it under scale arrow length there,
Where?
right there. You just have it under length, scale arrow length.
No, I don't think.
Hmm.
Okay, anyway, but I'm sure you can do that. Okay, let's move, start, go back. So the final images that one you have seen so far. Okay. Now the third one. The third one is the more beautiful example. The one we didn't have time to do in the lecture is the flowing cells inside a channel with a constriction and then an obstacle at the end. Okay, so this one, it's I will open here, open the again. Now we have the form. The particles, the cells are flowing from the right side of the left side of the channel. They are being created here at the very border of the region, and they are pulled towards this channel. So there is two things happen here. The cells has a speed to move to the right, and when the cells find the constriction, they have to squeeze each other to pass through. So the pressure on this region will increase while outside of this region will be smaller. The same happens here when the cells reach the obstacle, they will exert pressure of it, so its own pressure will increase, and they will move around the obstacle and pass through it. At the end, at the right end of the region, there is a kind of sink where the cells disappear. Okay? So we have pressure and velocity. So we have to include two two extra fields. One scalar for the pressure, one vector for the speed. And we have already learned how to do that, because you have to go to the steppable, add steppable drop-down menu, and to include two steppables. One scalar, the other, no, I don't know, let's see. One vector. But this is the usual way to do. Now, we are going to do this differently. In the drop-down menu, where is my steppable here? Let me search for it. Here. I will force the inclusion of the vector field and the scalar field by hand, not adding a new steppable. I will include the fields inside the steppable we will have. This E713 steppable is the one which was built when the channel simulation was built before. So I'm adding here at 2 lines those two extra fields, the vector one velocity and the scalar field pressure. I mean, we really don't need an extra steppable to include extra fields. Of course, if you are going to be more specific on dealing with the vector fields or the scalar fields, it's good to have a special steppable for each one. But here we only have to see the fields flowing of the flow. Okay, so I will add here the two fields, the vector and the scalar field. Okay, this is done directly from the extra field drop-down menu. A scalar field here, cell 11, and a vector field also cell 11. And both are in the init function, as should be. We are initializing the vector fields. So it must be here. Okay? So once you have done that, we again, as we need to keep track of the speed, we need the dictionary with all the entries. $713. Yes, the question is 713. Isn't it? Here, the name of the.
Yeah, you just referenced day 4 simulations. So I was pulling from that. Good.
Okay. So adding the dictionary entries for the old position of the center of mass, of the nucleus center of mass in the start function, the same as we did before, because we are interested in the speed. In the speed, we need two positions at different times. We are establishing the time interval between measurements as 10. And here we are creating also, we are fulfill the fields. Let's see, because at the step function, we are creating cells. Remember, I told you, at this part of the region, we are all the time creating cells to flow inside the channel, okay? So when I created the cell, this new cell is created here, And I have to keep track of all the position of this new cell that has just been created. Okay? Let's go back here. So, updating the fields. Now we have the step function. There is two green stuff here. It's sometimes comments. Comments are very good in the code, but when you are showing the screen, this green stuff sometimes keeps you crazy. So here we have full field, updating the velocity and the pressure fields. Okay. Field V, self-vector field V, field S, self-scalar field. Since I have a velocity and pressure, one is the vector and the other is the scalar. I don't need to put anything else here. Calculate the velocity here, the speed, again, using that algorithm, delta x, delta y, c, vel x, vel y, and the fields. This velocity field has to be filled with a three components vector, x, y, and z, and the scalar field only with the numerical value of the cell pressure. And then I update the dictionary with the actual position of the center of mass. Okay? So, in summary, we created two fields, the vector and the scalar, one for velocity, one for the pressure. Then, if a new cell is created, I have to keep track of the position of it, and then I updated the fields here. I filled the fields with this algorithm, pretty much equals to the previous one. Just now we have two fields to be filled. This the velocity and the pressure field. Okay. This is what we have done so far. Let's back here. The comments are here more. Here the comments are more. The layout is better to understand. Huh? The update of the fields and the update the dictionaries. Okay, let's run. Open player. Where's the player? There you have. Let's start over to see that from the beginning. One step only. You have the velocity graphic field here, the pressure graphic field here, and the cell field here. Put it to run. You have the cells appearing in the left side here, being created here. There is an external potential acting over the cells to flow. See, you have the cell pressure. Here's, I should have put a limit here. Let's see if I can handle this fields, pressure. I don't know if this is what I have to do. Here. See, now you have a better image for cell pressure at each cell position. I don't know why it's so red sometimes. And there you have the speed. See, the speed inside the channel is bigger than outside of it. And here, what happens when the cells, no, it's okay. The cells have a detour from the obstacle, which is this region here, which is here. Okay? So those are the tools I would like to show you today. So you have both scalar fields, vector fields with a color-coded image. Then you can really see what's going on inside your system with each one of the cells. Hmm?
I have a question, Gilberto.
Yeah.
So why is the pressure field so much fluctuating? Like I was expecting to something like a uniform pressure field before the constriction, a high pressure field around the constriction, and again a lower pressure field, and again a higher pressure field around the block.
You mean
So
that you
yeah,
should
yeah.
have some more constant values here?
Okay. So is it kind of like some stochastic fluctuations happening?
Well, you see, out of the cells, let's start to see if there are names. Why they are negative? Well, because some of the cells are growing and the others not. Remember, we have that control in our simulation, the function. Let me go back. I don't remember if this one has the function that controls the pressure. Is the other one. Cell, where is the pressure? Cell pressure is here. See, in this, remember when I explained the cell pressure in the previous lecture, in the other lecture, I showed how to calculate the pressure from the potential energy,
Yes.
volume energy. It's a derivative of the volume energy. But that is a manual way to do. CompCell has an intrinsic function that calculates cell pressure in the same way that calculates the volume, the surface, length, anything. This is, see, defined here, cell pressure. This is an intrinsic CompCell function, which is part of the dictionary of the cell, like volume, surface, and anything. Okay? So this pressure here is being calculated with that pressure, with this internal function. Now the question is, why the values are so negative? Let's see, where is here? Let's run for... The pressure will be negative if the volume tends to be smaller than the real volume. The target volume is bigger than the real volume. So it's a kind of fluctuation, I think. Just of the temperature, the membrane fluctuation, the acceptance rules of the evolution of the Potts model. I think that's it. Maybe you should limit this.
Yeah, I think James pointed out that pressure is very noisy because of the stochasticity in the movement. We can average the pressure over a few times.
Yes, maybe. Yes. Okay. May I go on? Are you satisfied or not? Well, let's.
I think it's important that you show the adhesion flex, so I would
Okay.
encourage you to move.
Okay. We can talk later. Who are your name? What is your name? Okay. So let me go on and continue here for the next topic, which is the AdhesionFlex plugin. In this plugin now, I'm just telling you how to use it, and I'm not going for a very, very fancy model, nothing like that, not fancy simulation, not like that. I will just introduce the motivation for it and how to use it, okay? Okay, so when you talk about cell adhesion, we have lots of complicated mechanisms, which can be between cells or between cells and the substrate where they are moving on. Okay, we have these very complex kinds of interactions between cell and cell here, and the cell and extracellular matrix here. Okay, and each one of these interactions here are mediated by different cell molecules, adhesion molecules, what we call CAMs. Huh? They can be integrins, immunoglobulins, something adhesion molecules, selectins, caderins, lots of different adhesion molecules can be taken into account for to study to reproduce some system. So we must have in mind that is in the surface of the cell it has molecules, adhesion molecules with different densities, and that should be available for CompuCell 3D to reproduce. Okay? This is, in general, we have using so far the contact plugin energy. So you at the beginning of your simulation, you define the type of the cells, and then after you have to fill adjust a matrix of interactions between cells, the contact energies. But now we are going to do a little bit different, and we're going to use the AdhesionFlex plugin. The AdhesionFlex plugin in its mathematical expression is this one. Remember, I don't know if you remember. The contact plugin uses the energy as a constant term in parentheses here to specify the interaction between two kinds of cells, always the same way. And now we have the parentheses replaced by a sum over a function which takes into account the density of each kind of molecule you are including in your simulation with a specific rule of interaction between them. So you can have 3 or 4 kinds of molecules, and these three or 4 kinds of molecules interaction of each other, or interaction with one interaction with all the 4s, or 2 interaction with 3 others, and so on. There is a big mesh of interactions, a big network with interaction between the 4 kinds of molecules you add into your simulation. And this is summed, the resulting effect of all these molecules is implemented by this kind of function here in parentheses. This, of course, you don't have to implement it by yourself, because this is what CompCell does intrinsically. We have to define the amount of the densities of each molecule in the surface of the cell, and what is the intensity of each kind of interaction between both each two kinds of cadherin. I mean, if you have cadherin 1, cadherin 2, this has an intensity F. If you have cadherin 1, cadherin 3, you have another interaction of here. And we'll have to sum all over these interactions to get the result for your simulation, which CompCell does. Huh? So let's have a look. So we have to specify now, no, not now, sorry. In the contact energy, you specify the J's, that matrix. But now, well, talking to the J's, the J's is if you increase the number of cell types, you increase the number of J's as any types square, because you have a matrix, remember? A square matrix where you fulfill the matrix with the J's between different kinds of cells. Now, we have to specify the densities of the molecules. Cadherins, integrins, or whatever you want, between cadherins in between pairs of cells, or integrins between cells and the extracellular matrix. That means that now the medium can have more than one molecule as well. Okay? Because the medium can have diluted a substrate instead the medium can have different molecules built in it. So the contact energy is that. The AdhesionFlex now is that. So let's go a little bit more in this fraction. Kmn is the strength of interaction. F now here is a function between the densities, which says how the densities play with each other. And N and M, Nm and N is the dense. See, the delta function, that delta Dirichlet function here says that if you are dealing inside the same cell, there is no contribution for the adhesion. Okay? This is only one if I is different of J. Huh? Okay. Let's go to the
Let me,
cell for the example 714 again.
Gilberto, sorry to interrupt, but you have about 15 minutes before we're supposed to go to break.
15 minutes more?
Yeah.
Okay.
15, 20 minutes.
Yeah, okay. I can handle that. No
Okay,
problem.
great.
So let's close this one. And I will open now this 714. What? It didn't open. Where am I? Open. Where am I? Let me check here just a second, guys. What's going on with the project? I think I have to close to edit and open again. Project, open. Okay. Here. This decrease the thing. Okay. So look, now instead of load at the beginning of simulation the contact plugin, you have to go for the AdhesionFlex Plugin. Okay? So I forgot to mark here. We are going to load the adhesion flex, the volume flex, and the surface flex, and the center of mass plugin. Okay? Well, you can find the simulation ready to go in your demo codes, and it is here. Okay? So we have two kinds of cells. Cells dark D, light L, in a 25 blob radius in a 100 by 100 by 1 grid. And we are going to make them interact with two adhesion molecules. I will call this CAM1 and CAM2. Okay? So after when you are loading this molecule to edit the wizard, after you choose for the adhesion flex, let me see where is that here, the adhesion flex. No, it's a plugin. So it must be here. Here. See, it will put here in your simulation this block here is a kind of big one. With the types you have to include, CAM1, CAM2. We have to define the density because each cell has both adhesion molecules, 1 and 2. So here we have to say that the cell's kind D has density 6.1 for the molecule 1 and 4.1 to molecule 2, and the cell type L 2.1 for 1 and 3.1 for 2. Those values are already being adjusted. This is that boring part you have to do when you are planning your simulation. And you have to stabilize. Remember the formula I showed before? Here, this formula F here, it's a function converting the densities in contact energy. This formula is here. It's a special entry in the plugin. It's called binding formula. Name binary. You can choose another one if you want. You can put everything you want here. You can put a mathematical expression here that involves molecule 1 and molecule 2. In this formula here, I'm saying that the minimum of molecule 1 and molecule 2 should be taken into account when they are I'm comparing two cells and two molecules. For example, I will have this. If molecule 1 is 6.1 and molecule 2 is 2.1, the value here will be put to 2.1, which is the minimum value of 2 and 6. This is the value which will be used contact energy for this specific encounter of two densities. Okay? And the intensity, the strength of the simulation, and also is here, this K Mn, see, if you have two molecules, you have molecule 1 with molecule 1, 1 with 2, and 2 with 2. And you have to fill these strengths with some values. Those are also chosen for you. Okay, here is the blob initializer where the initial state is created, and then you can produce now as run in the see, you have here. Let's start over to see how is the first step. The beginning is that. See, remember when we in the blob initializer, when you choose it, I put D, comma L. I'm saying that the initialization must be 50% of each cell, each kind of cell. So put it to run, and you have the sorting process going on here. Eventually, the cells will merge together in an inner blob rounded by the yellow cells. See? It has basically the same effect of the contact energies, but now you can play with lots of different molecules in your simulation if you have to include them. To see the competition between different molecules, between molecules among cells and cells and the substrate. To see what they interact with the substrate, for example, in a cell crawling movement. Huh? So this is what I have to I would like to have to show you in this adhesion plugin, how to manage it, how to handle different numbers of adhesion molecules in your simulation. This is the way to do. Okay? To finish this presentation, I would like to show you some here is all the thing I passed through because of the time. So you have these things. How to make a movie with CC3D. We have seen, I think, in Pete's presentation, he went through a movie make tool. But let's do it again here. I think with a little more details. Huh? So, to make a movie, after your, let's say again aqui, after your simulation begins, you click one step function button here, quick step button here, and you click in this small photographic machine here. When you do that, your CompCell creates at your simulation folder here, let me show you here. These two subfolders, the screenshot data and the cell fields 2D XY0 folder. Those are the folders where your images will be saved. What images? The simulation images you need the snapshots you need to make the movies. But how do you create the snapshots? You go here in the configuration preferences, and you have this tab, screenshots and movies. You say here, save image at every Monte Carlo step. Then you choose here how many steps you want to be you have to simulation saving snapshots, 150, any number. The resolution, you can adjust the resolution of the step of the image, and okay. When the simulate starts now, at each Monte Carlo step, you have a snapshot of this, the screen, of the cell field screen here, okay? And those images are stored in this folder here, like that. And the cell field have a bunch of it. I let the simulation running there to create the images, okay? After that, when your simulation stops, I will stop the simulation here. You go again to configuration, screens removed, and go to create movie now. So you have to find out here what is your last simulation. I think it's this one, the one we are running right now in the player that I have stopped now because of the time. See, the simulation is 11, 24, 26, I think is this one. Select the folder. Just click in the folder here and select it. And click OK. No. See? Two movies, I don't know why they create. I think I create twice. I clicked twice. This is why I had two movies created successfully. Okay. So once the movie is created successfully, they were created in a folder. Let me put OK here to close, which has the name movies. When you click it here and create movie now, this subfolder is created, and inside it you have your move created. So to see the move, go to the configuration again, show move in file browser. This will open the file browser here with the two movies that I just created in MP4 format. Oh, you click on it, you have your movie ready to go. This is very handy now. Before this version of CompuCell, you have to do this by hand. Open a movie maker, copy images, select the time interval between images to move. It's a very painful thing to do. But now it's very easy to do. Okay? So this is a very handy tool for your simulations in CompuCell 3D. And finally, the last thing I want to show you is how to save data, how to store data in CompuCell 3D. Okay? And this is another project which I called 714 Write. Okay, let's see. First, to save your data, you must create a file. You must create an algorithm to create the output files and then writing them. Okay, so let's say this following. Suppose we want from the previous simulation, from the self-sorting simulation, I want to follow what is going on if a cell ID number 40. Just pick one, okay? So for these cells, I will follow it, and I will keep track of some fixtures of it. But now we have to here in the green line, I call an intrinsic function of CompuCell3D, which is the self-output dir. Self-output dir gives you the current folder where your simulation is. The current folder of your simulation. Okay? You can change it if you want. If you want to do that, please. If you want to save your simulation in other places, you have to change this value in your wizard, when you build your wizard, in the location of files, remember? So I'm creating inside that location, the self-output dir, I will create a new file which has as a header the folder and something that identifies the cell I'm trying to follow. Cell ID number 40 and some information about the grid where I am running my simulation. Grid size. And I will use this internal function of CompCell self-dim_x that gives you the x length of your grid. Okay? So now I'm creating the file name of your simulation. Self-data is that part of if a string here, dir cell ID grid size plus cell data dot. This line creates the output file name, the complete output file name. Remember, when you run the simulation, you must want to keep track of what the data of your simulation is really giving you, what kind of simulation, what parameters you have used, everything you can put in the name of your output data. I mean, you build your output data name, file name, with parameters of your simulation to be easily identified later. Because when you are running simulations, you're running all the time. You are adjusting parameters, you are changing parameters, you are changing setups of your grids, everything. And a bunch of data comes out. So you need to identify this bunch of data with parameters in the names of your simulation. And you can build the name, transforming some parameters in strings and adding it to the name of your output data, output file name. So here I am creating this variable, the file that opens the file that I just create with the name self-data with the option W. This means that I'm creating this file for the first time to write. Creates the file for data write access. And in this line here, I am writing a line with the header of the output. I'm saying that the columns inside this data file are time, cell surface, and cell volume. And I close it. Why do I close it? Because I want this data to be immediately stored in your hard drive. If you keep your file open, the computer will decide when it closes or when it stores some information in your hard drive, because the computer needs to fill some buffers when the buffers of output is filled, then he stores in the drive, and then starts to fill the buffer again. So if your computation, if simulation stops for any reason, you will lose everything if you don't have it saved before. Okay? So this part of the simulation is in the start file. I created the output name, I created the output file the output file. Okay? Now in this here, I will write in the data file the output I want. So I run over the cell list and search for the cell ID number 40 that I was trying to follow. And so when I find that ID 40, I reopen the self data, which is the output, and I write in this format. See, this is Python, how Python uses format. D is for integer and F is for float. So I'm writing free formatted the MCS, and with eight numbers the cell data, and with 8 numbers the cell data, no, sorry, the surface data, and 8 numbers the volume data. And this is the list of what has been saved in the file. And again, for each time that I write, I close to be sure that I'm saving the output right away. Okay? So let's see. This is included in here, see? Everything that is there, it's here. In the exercise that I called 714 write. Here is the output. Okay? So if I put it to run, just finish. Running player, it will save the information in the data file. And this data file, now I have the simulation is running here. I will stop. The data file now is, let me search just to show you where is the data file. Okay, I should start here. I'm not losing time more because see, the simulation will create the file name as this one, see? This is the self output GIR to here. That cell ID is the thing I added, equals to 40. The grid size is 100, and cell._data. And the content of this file is this: time with the header, time, cell surface, and cell volume, the header. And for each Monte Carlo step, there is a line containing the time, the surface, and the volume, and so on. Okay? So I'm happy you have enjoyed this presentation, and please take a minute to fill the questionnaire. Thank you, and nice to have you here during this workshop. See you.